So this is the constant velocity lab. Constant velocity is the same speed and direction of an object, and the purpose of this lab was to create an experimental model of an object rolling at constant velocity, and then build a computational model of an object moving at constant velocity as well to compare. To do this, we can use Newton's second law, where the final velocity is equal to the initial velocity plus the change in acceleration times the change in time, which describes the relationship between forces acting on an object and its acceleration. So if the net force of an object is zero, then the velocity will remain constant because there's nothing acting on the object to change the acceleration. This practical required two parts. There's the experimental, which was taken from observations from recording a ball rolling and using tracker to analyze it, and then the computational model created using GlowScript. So I used a 0.12 kilogram ball of yarn that had a diameter of 0.11 meters and recorded the yarn ball rolling at constant velocity for approximately 2 seconds, and then used the program tracker to analyze the position of the ball per frame in those 2 seconds. The computational model was created using Python coding, as well as the initial velocity of the yarn ball from the experimental video. And then as a result of this practical, I found that the computational model and the experimental model had a positive linear relationship that changes as time goes on. So this was the video I uploaded into Tracker of the yarn ball. I calibrated the program to the size of the yarn ball, which again was 0.11 meters, and then set my axes so that the yarn ball was moving in the positive direction. The yarn ball would be considered the system, and then the carpet and everything else would be the surroundings. And then I chose the position points in every frame for approximately 30 frames of the 2-second video for my X position, which can be seen in this table down here in the right corner. And then for the computational model, I changed the code here so that the ball was the accurate mass, even though because we were using constant velocity, that didn't actually end up mattering. And then I found the initial position of my object from the experimental object that was computed by Tracker. So that was at the X position was 0. And then because the timestamps between frames was 0.033 seconds, I chose the computational model to have the same delta t. And then to compute the constant velocity, I used the position at 0.03158 meters at time 0.033 seconds, which was ended up being 0.956 meters per second. And then this was the conditions for the while loop, which was used so that the program could iterate until it reached where t was equal to 1.034. And then after that, the loop would stop. And then to update the velocity, the variable ball.vel equaled itself plus the acceleration times delta t, but because acceleration was 0, it ended up remaining constant during the while loop. And then the same thing was used for the position, where the velocity times delta t was added to its current position, and then time was updated by adding the current time plus 0.033. And then at the end of this loop, it would print the time and the position of the ball until it reached where t was greater than or equal to 1.034. And then these figures were created in GlowScript, where the first image showed the position time graph, where you can see the position increased linearly. The second image was the velocity time, where you can see that the velocity remained constant at 0.956 meters per second. And then the last image shows the position of the ball over time, where you can see that it was moving in the positive x direction. And then I combined both of these sets of data into one graph so that we could compare them. And in this position time graph, the computational model and experimental model have a linear relationship and follow the same line. And then around 0.05 seconds, you can see the lines begin to split, where the experimental model, which was shown in blue, begins to have a negative change in slope, whereas the computational model, shown in red, has or continues the linear path, which makes sense because the yarn ball in the experimental model would experience friction from the carpet, meaning the net force acting on the model would not be zero. And the computational model is in idealized surroundings, so the ball would continue moving linearly with no change in slope. If I had chosen my axis so that the ball was moving in the negative x direction, then the position time graph would be in the fourth quadrant, where time would still be positive, but the slope of the line would be negative because it's moving in the negative direction. However, the linear relationship would still be the same. And then one way that the experimental model could have incurred error was the material of the ball. Since it was a yarn ball, the object was not completely round, which would affect the way it rolled and constant velocity. And it was also rolled on carpet instead of like a hard surface, where the force of friction could potentially have been greater between the materials.